Okay, so the total power consumption of the circuit, you'll use the total power, the total current and the total voltage drops. And so we could just substitute in here. We'd have the total current of 0.277 amps and the total voltage drop of 12 volts. And so then 0.277 times 12 is 3.324. 3.324 watts. Now let's do like we've been doing stuff, throughout. That would be the answer, but let's go ahead and finish out our VIR chart just for practice. So then we would have, let's see here, total current. Okay, so R2 and R3 are in series with each other. Now they're going to have voltage drops that add up to equal the same voltage drop that you're going to see in R1. So if I highlight R1 in purple here, and then I highlight R2 and R3 together like this, then I'm making a note to myself that those, whatever goes in those purple boxes, these two are going to add together to give me that number, that same number there. Then the current, whatever current is going to go through R1 is going to add together with the current that takes the R2, 3 path. R2 and 3, I'm going to put a little purple equal sign here, a vertical equal sign to show that they're actually going to have the same current flowing through them because they're in series with each other, one right after the other. And so if we find the current that goes through either one, we'll find the current that goes through both of them. All right, now you can also use proportions. So thinking about the R2, 3 path, the R2, 3 path has a total resistance of 50 ohms, whereas the R1 path has a total resistance of 100 ohms. And electricity likes to take the path of least resistance. So since basically this high road here has twice as much resistance as this low road, you're going to have twice as much current take the path of least resistance. You're going to have twice as much current take the low road. So how can we take our 0.277 amps and split it so that we get two different currents, one of which is twice as much as the other one? Two different currents, one of which is twice as much as the other one. Now mathematically, just to practice writing things in math language, that could look like this. So you'd say your total current, and then this is Kirchhoff's junction rule, where the current is going to split at junctions and recombine at junctions, and you're going to have, you're going to be obeying your law of conservation of charge, where current is your flow of charge. So your total current is going to equal the current that flowed through R1 plus the current that went down the 2, 3 path. And we know by proportions that the current that takes the 2, 3 path, the I2, 3, is going to be twice as much as the current that takes the 1 path. So how do we say that mathematically? The I23 is or equals twice as much as the I1, or 2 times the I1. And so this allows us to get rid of two unknowns. Whereas we can say that I23 is 2 times I1, we can actually put in 2 times I1 in this thing's place. So we can say that I total is equal to I1 plus 2 times I1. And we know the I total is 0.277 amps, and so we can solve for I1. And so 1 I1 plus 2 I1s is 3 I1s. And so we can divide both sides by 3. And so 0.277 divided by 3 is the current that takes the I1 branch. 0.277 divided by 3. And so the current that takes the I1 branch is 0.092, and then 3 repeating, and I'll just leave it at 0.092 amps. That unlocked up here 0.092 amps. Now I can go back to my earlier equation. I can put in 0.092 amps for I1, and I can calculate my I23 by just subtracting 0.092 amps from the total. So 0.277 minus 0.092 is 1.85 or 0.185. 0.185 amps are left over to take the R23 branch. And so they're going to have the same current flowing through both of them. So we can fill in both of those rows. And then we can use VIR now that we've unlocked 2 variables on each row. And we can do, to find the voltage drop across R1, we can do 0.092 times 100, which is just going to move the decimal over twice, and we get 9.2 voltage, 9.2 potential difference, voltage drop. And then 30 times 0.185, so 30 times 0.185 is 5.55 volts. And then 20 times 0.185, 20 times 0.185 is 3.7 volts, 3.7 volts. And then to double check what we highlighted in purple earlier, the 5.55 volts plus the 3.7 should add up to equal the 9.2 that we had earlier. And with a little bit of rounding going on, they do add up to even that out. So that's good. And then 9.2 plus 2.77 should add up to be 12. 9.2 plus 2.77 adds up to 11.97, but we've had some rounding going on. So that does basically add up to be 12. So we can verify that we've done everything correctly along the way. Now let's just see who's the brightest bulb in the box, and we'll be done. So let's switch to like this yellowish color here and do our PIV work, I times V on each row. So we're going to do 9.2 times 0.092, and we're going to get a power in R1 of I don't need any. 0.8464. I'm just going to round that to 0.85 watts. And then I'm going to do 0.185 times 5.55 for R2. And I'm going to get 1.03 when I round it. My calculator said 1.02675. And then I'm going to do 0.185 times 3.7. And I'm going to get 0.6845. I'm going to just round that to 0.68 watts. And then 0.277 times 2.77. And I'm going to get 0.76729 watts. I'm going to round that to 0.77. Adding all those together, we'll get the total power. So 0.85 watts plus 1.03 watts plus 0.68 plus 0.77 watts. We're going to get 3.33 watts. Verify by doing your total voltage times your total I, and hopefully you'll get 3.33 as well. So 12 times 0.277 is 3.3 also. Now let's rank the bulbs, and we're all done. So who's the brightest? I'm just going to write this in here. To the dimmest. And we're just going to rank them by the powers. So the brightest is going to be R2, greater than R1, which is greater than R4, which is greater than R3. Okay, we did it. We can now do the craziest of the crazies. All kinds of combination circuits, finding brightness of bulbs, powers, resistances, collapsing circuits. Oh my goodness. Okay, so thanks for hanging in there with me. And have fun working on some more of these tonight. And happy physicsing.